Good morning to you all. So last day we have discussed about what is artificial neural network. We have seen the McCulloch model and the synaptic connection that mathematically defines the real biological neuron. And then we have discussed about different types of activation functions, which is very much crucial for learning artificial neural network. And so these three are actually very well known and popular activation functions. We use it very frequently in our programming purpose. Now also we have seen that how, as an example, how we can implement a linear regression problem using artificial neural network, and then we have realized the error curve with respect to the different types of uh, the initial weights of the initial synaptic weights of the network, and we have seen that ultimately this particular ball that is representing this initial weight. You see, this initial weight actually can be somewhere here, maybe somewhere here, or maybe in this side also. It can be in this side also. So it totally depends upon, ultimately this curve is an error, curve of the error. And this is the weight, and cost is nothing but the error, actually. So whatever the initial weight may be, you will be either in this side or in this side, and ultimately my goal is to decrease the error between the desired output and the actual output. So I want to come to this point here. So if I am in this part, I will come in this direction, and if I am in this side, then I will come in this direction. So, and how we can do this? That is what actually we call gradient descent algorithm. So last day we ended with this slide. So today we will go through the gradient descent algorithm, which is a learning algorithm for the artificial neural network that will basically tell you that will basically define that how this ball that is representing the weight is getting updated its position and come to this point where I have a global minimum. Anyway, so let's dive into the gradient descent algorithm. So you see in the left hand side what we have, it's a generic artificial neural network is given, that these three are actually representing three neurons that is in input layer. So this is an input layer, and these two are also neurons which are presenting in some output layer. Okay, so it's a two layer artificial neural network, and this x1 x2 x3 is nothing but the the value that represents this particular symbols. So basically we have input through this neuron, something like this. Okay, so I mean that means this x1 has some value, x2 has some value, x3 has some value. So, and these values will get propagated to the output, and finally some output will be generated from this particular neuron. So if this is an output neuron, so I'm expecting the output from here, which is y1. So similarly we are expecting the output from this neuron, which is an y2. Now this is what we can say a forward propagation. The input is fed into the input layer, and then it transferred to the output, and some output I got. So that is what we call forward propagation, and after this the learning actually will start, in a sense that the error has to be calculated first, because one thing we have seen that in case of artificial neural network, the type of learning algorithm, a type of learning it actually follows is a supervised learning technique, because we have some already given some result or desired value that I know, and I'm getting some value that are some actual value. So it depends on the error, I'll basically change what? I will change the synaptic weights, that is W11, W12, W21, W22, W31 and W32. These 6 synaptic weights of the neural network, which are actually the free parameters of this particular model. So that means one thing is sure, that we have some desert, say D1, for this particular output neuron 1. So, and similarly we have some D2, that is for this particular output neuron. And what actually happened, we have a subtraction between this desired and actual, so that we can find out this error. Similarly we have something like this over here also. So we have some difference between, you have to find out the difference between here and which is E2. So this E1 and E2 are actually represents how how much deviate you are from your desired value, and depends on that basically we have to change this synaptic weights. Now see, ultimately with respect to this particular diagram, one thing we have seen, that since this is a curve of the I'm sorry, this is the curve of the error. So one thing is sure, that this is your the gradient of the the curve of the error. And you see, since we are going downwards, if you in this side you are going in this direction, and if you in this side you are going in this direction, so basically what you are doing, you are actually going against the gradient of the error curve. So that's why we call it gradient descent. Now question is that gradient of what? Gradient of the error. Now why this error has been generated? The error has been generated because of this synaptic weights. Because if I assume that I have the synaptic weights that is initialized over there are correct synaptic weights, that means I should get exact value in y1 that I want. But if I am not getting that exact value, sorry, I must have arrow over here. If I'm not getting the exact value that I want, that means these synaptic weights are wrong. So somehow I have to update these synaptic weights so that we can get the better result for the next pattern. So that means we are trying to, we are trying to go downward towards the gradient of error, that is with respect to the W. Now, if you come to this point, this particular point, where basically you will see that there is no change of this error. There is no change of this error. So that means naturally I can say that this DEDT will be 0, where DEDW will be 0, right? So let's see what actually we have defined. That's why over here we have defined the total error with this equation, that is half summation over j equal to 1 to 2 tj minus yj whole square. So it is what you can say a sum square error, right? So t is, why j equal to 1 to 2? Because with respect to this particular example we have two output neurons, so this j is representing jth output neuron. So that's why j 1 to 2 tj minus yj whole square. Now why this half is given? Actually this half is given just because of keeping the total mathematical computation very simple. You will realize it very soon why the necessity of this half. Okay, now this is just a constant, so it doesn't matter that whether it is half or 1/4. Anyway, so ultimately that we have seen that we have to find the gradient of the error with respect to, that is wij, right? And ij can be what? What is I? I is basically the input neuron. So with respect to ith input neuron and jth output neuron, the synaptic weight that we have considered it as wij. For example, from first input neuron with the first output neuron, we have w11. For second input to first output, I have w21, something like this. So that's why it is representing wij. Fine. Now you see, if you watch this particular equation 1 carefully, then one thing is sure, that this particular term doesn't contain any wij right now. So if you try to directly if you want to find the derivative of error with respect to wij directly from this equation, it will be pretty tough. So now what I can do, we can apply a very interesting property of a differentiation, that is chain rule. So what we can say, that this error is directly directly function of this yj, and this output y can be written something like this, in this way. This is the equation 3. Okay, so that means I can easily say that I can have a chain rule where I will find the derivative of error with respect to yj, and that yj with respect to wij. So if I do in this way, and one thing is sure, that if you want to find out the derivative of this derivative del del iyj, we will find out this equation. Why? You see, if we just elaborate this situation over here, basically here e is what with respect to this example? This is basically just ignore this half right now. Okay, let's keep this half. Let's keep this half, and then we have t1 minus y1 whole square plus t2 minus y2 whole square. So now if you do this del e to del y, say say for example y2, okay, del e del y2, where j is representing 2. Now what will happen? In this particular term there is nothing related with y2, so it's basically 0. It will become 0. But this particular term contain y2. So what will happen? Here also we have a very interesting chain rule of differentiation, that we will have something like half into 2, then t2 minus y2, and then differentiation of this one minus differentiation of this one. So this is a constant term with respect to y2, but so d e dy2 with respect to minus y2 will be minus y2, minus 1, sorry. So this 2 will get cancelled out, and that is why you see now half is given. If you don't have this half, this 2 will remain over here. So that's why maybe in future the situation will become little bit complex. To make this simpler, we have used this half. So ultimately it become minus 1 into t2 minus y2, that means minus t2 minus y2 for de dy2. Now if you consider with respect to in place of 2, if you consider yj, it will become tj minus yj. What is given in this side? So that means derivative of error with respect to yj will be minus tj minus within bracket tj minus yj. It's very clear. And also we know that what is yj? That is multiplication of the x's with respect to w and their additions, like x1 into w11 plus x2 into w21 plus x3 into w31, and some activation function over there. So now if you write this one over here, we can say that okay, so yj can be written directly something like this if we forget about activation function right now, and then ultimately This, if you want to find out dyj with respect to del wij, you see that for specific wij, one wij will left and other wij will get cancelled out. For example, if you want to find out del y2 with respect to del 2 1, I'm sorry, say 1 2, suppose I is 1 and j is 2, so del y2, I mean you want to find out dy2 by dw12, so what will happen? This dy2 means x1 into w11 plus x2, sorry, x1 into w12 plus x2 into w22 plus x3 into w32, that is y2. So naturally, if you differentiate this y2 with respect to w12, only w12 will be, will not be constant at that time. Other w's, that is w22 and w32, will get cancelled out because they are constant with respect to y, with respect to d12, I mean w12. So ultimately what will left? Only w12 with xi from where it's coming will left, that is x1 in this example. So, and then obviously, I mean, if you differentiate it, that w12 will get cancelled out, and then xi will left, that is x1 will left. And what is x1? So with respect to x1 is nothing but from where this w12 is coming. So that means with respect to, if you just convert this example with respect to ij, instead of wij, this wij is coming from ith neuron. So that's why xi will left. So that means dyj by dwij is xi. Now these components I have find out, these components I've got. So I can easily compute this equation. So this is what, I'm sorry, just a minute. So this is what the equation for the derivative of error with respect to wij, and with respect to this error, I think you can easily, one thing clear is that, you see, now question is that what is the initial weight of these w's? I mean, is there any rule? Practically there is no rule, because you know this w value can be anything from 0.001 to 100, doesn't matter, because depends on these different w's, whatever error will come, it will be either in this side or in this side, somewhere in of this side, whatever, it doesn't matter. The mathematics is designed in such a way, if they will actually go downwards against their gradient, and by mathematical equation a time will come when this particular error point will be stable in this side, in this point, where the error I can consider minimum or maybe almost zero. So, and this is a very beautiful property of a artificial a gradient descent algorithm, or you can say a neural network seed problem, that neural network learning algorithm or the outcome doesn't depend upon the initial weight of the model. You can choose any initial weight. So generally, in in a you can define within 0 to 1, but it does not mean that after learning the all the errors will be remaining under within 0 and 1. If you watch the changes of the weights carefully, if you save those weights for checking how they are changing, in some cases you will see that you have started with weight say 0.01, and it went to maybe 100 or maybe minus 100 or maybe minus 500, doesn't matter. It is not in your hand, because the artificial neural network will decide, depends on these mathematical equations, that what will be the optimal weight of this synaptics, so that ultimately this y1 and y2 can generate the exact result that we want. Now, naturally, ultimately, what we have got, this is del E del wij. Still, weight has not been updated. You see, the weight updation del wij, this is what we can define in this way, because this is basically the expression of del wij, and this is eta, what we call learning rate. And what is learning rate? We have already discussed that learning rate in my previous classes. So let's discuss once more. For example, that if I take a data structure class, there are two possibilities: that I will take a chapter for say 2 or 3 months. In that case, what will happen? That on time your syllabus will not get completed. So whatever learning you had, only you'll have a very small amount of learning. Whatever the data that I have given, I have told you, you can understand that, but you have a major portion, you don't have any idea. So if you want to give exam after the end of semester, you may get failed, because you don't have any idea about major portion of the subject, because I was too slow to teach you. Actually, you were too slow to learn it. In other side, if I say complete the data structure subject within say 7 days, what will happen after 7 days? If I tell you that just give an exam, and if you want to solve the problems, you will see it's not possible, because although you have completed everything within 7 days, but your speed was so high that you cannot able to realize what actually you have learned. So in that case also you will fail. So in these both situations there is a possibility of failure for the exam, because in one case learning rate was too slow and in one case learning rate was too high. Similar situation you can assume for a artificial neural network. If you and the exam that we are actually discussing in this example is nothing but, you can assume that the case of testing, you have two data sets, training data and test data. So they are two different data set. So data that you have used for training, after training that, when you will test it with a test data set, what will happen? The neural network will give very poor performance, very poor accuracy. The result with respect to exam in your side is nothing but here accuracy with respect to the side of artificial neural network. Whatever, but in both cases we have a possibility of poor test result, although I have trained it. Why? Because ultimately we had very small learning rate and very huge learning rate, so nothing is expected. Your learning rate should not be too small, your learning rate should not be too high. It should be optimized in some value. Generally we keep it from 0.01 to 0.1 or maybe 0.2. Not maximum of that, but there is no guarantee. Actually what will be the best learning rate value, that is a little bit trial and error, part of trial and error method. You should check with various learning rate values so that you can find the best learning rate for the, I mean actually best learning of the model. Now typically we consider it in between 0.01 to 0.1, not more than that and not below that. Now again I am saying it is not a rule. The value can be lesser than 0.01, even more than 0.1. However, now see here one thing is not present, that is the negative sign. In previous side we had a negative sign over here, right, which is vanished over here. Why? The reason is that since you are going downwards against your gradient, so your direction should be negative, right? So that means when you will define this del wij, you have to consider that it's actually minus. So since already I had a minus over here, another minus will get cancelled out, and finally I will get this equation. And so this is what my weight correction, and that will be added with the old wij. We'll find the new wij for the next pattern. So if we now let's do one thing, let's take an example. By the way, the model that we have discussed over here is actually a single layer perceptron. Okay, what we call single layer perceptron. Single layer perceptron means there will be only two layers, input layer and an output layer, and they will get connected by the synaptic weights. Okay, so we can see that it can capable of learn linearly separable patterns. So we will see in an example something like this. So your data set will be something like this. So suppose that I have a data set of 4 patterns, and these weights and lengths are what? These are actually the features. You can assume them as a feature, and you can see that they are in 2 different classes. The weights are defined in such a way that they are in 2 different classes. Okay. Now with respect to the graph, if we draw the graph, you see these 2 should be in one class and this should be in another class, right? So what is our goal? Our goal is to train a single layer perceptron model using the above parameters to classify the 2 fruits, and then we can try to find out the model parameters to classify an unknown fruit having weight 1.40 kg, I mean sorry 0.140 kg, and maybe length will be say 0.179. I mean point will be not present here, will be somewhere here. Okay, so now that means from this graph one thing is very clear, that I can easily draw a linear separable pattern, I mean a line that can basically differentiate these 2 points, and ultimately my goal is to find out what is the in which class this new fruit belong. I don't know the class of this fruit having weight 0.14 and length is 0.179. Maybe, if I assume the fruit is somewhere here, suppose the new fruit is somewhere here, so naturally I will say this is in class of this, right? But to realize it, what we have to do, we have to first find out this particular line. Now finding out this line means what? Finding out the parameters of the line, so that mathematically we can understand where the exact exact line present. Anyway, so let's see. So as we have seen, what is the learning step? We will initialize the weight matrix W that we have seen, and depends on that maybe I will start from either this side or maybe this side, doesn't matter. So now we will have a forward propagation of the pattern I that we have seen. The first pattern, the first fruit. Maybe from fruit 1 to or fruit class 1 or fruit class 2, doesn't matter. And then compute this actual response. What is this actual response? This is actually, this actual response is actually that yj, and calculate the error. And why, how it is possible? By tj minus yj that we have seen for various j's, right? So j is the number of output neuron in the output layer, and then calculate this wi del wij, that is the weight between ith input neuron and jth output neuron. So if you have followed my previous slides, the lecture from the very beginning, I hope now you can easily understand how we can calculate this del w. It's very straightforward issue. And then adjust this weight matrix. What does it mean, adjusting? Adjusting this weight matrix mean this equation, this one. Adjusting this weight matrix mean this equation. So basically we will find out the new value of wij by adding wij with del wij. Okay. So let's see. And then I equal to I plus 1. Why this I? This I is basically representing the number of patterns. Okay. And then go back and then go back to step 1. Go back to step 1 means, I should not go back to step 1. Rather, I should go back to step 2. It is not true. I should go back to step 2, because initialization of the weight matrix will be never come. Will never come. So we have a loop between this 2 to 7. Something like this. So that means one thing is very clear with respect to implementation of the learning algorithm of artificial neural network. It is just as a for loop, something like a for loop. Within the for loop, we have to execute some specific set of steps which is very clear to you. If you just mathematically write those equations, you can easily find out a learned model for evaluating the position of some unknown points. For example, in this case, this fruits. So now let's take an example, something like this. By the way, one thing is missing. In this particular data set, one thing is missing. That is, we have defined the features, but we have not defined their class labels. I'm saying that they are in fruit class 1, C1, fruit class C2. But when you will start writing or program, or maybe your program will start getting executed and take data from the data set, at that time, before we compute the actual response and find this target tj minus yj, what is tj? That we have not defined, at least in this example. This tj is that class level. So now this class level you can define in your own way, depends on the activation function you are taking. So since this is a very simple problem, a very trivial problem, that's why we have considered the class level as +1 and -1. +1 for one class and -1 for one class. Now since we have only +1 or only -1, not no other data in between them, that's why we have considered this signum function. And I hope you have idea about this signum function. We have already discussed in my previous subclass. If you don't have any idea about the activation functions, you can check those in my previous lecture video. And we can see the signum function is nothing but yi equal to either +1 or -1 if this vi is greater than equal to 0 or lesser than 0. So there will be no other value between +1 and -1. Fine. And now what we have to do? We will take the first pattern that we have seen, the I will start with forward propagation. The step number 2, you see the forward propagation of pattern I. So the first pattern is taken, and there is an arbitrary weight W. W11, W21. Now another question is that how many features will be there? Obviously there are two features, that's very sure, because length and weight, there are two features is present, and beyond that we have one more thing that we have discussed, that is bias. This bias also I have discussed in my maybe the previous class, so you can go through that if you have some I mean don't have the proper idea about it. So this bias has to be there. So that's why that mean it's a single layer perceptron problem where we'll have some input layer and an output layer, and this input layer will contain three input neurons. Among these three input neuron, one input neuron is fixed with value +1, that is representing the bias, and another two input neuron is taking the feature value from the class. So that's why these two are input uh, to the this 121 and 16.8 are two inputs to this neuron x1 and x2, and this w11, w21 and w31, these values are entirely arbitrary. I don't know what should be the exact value of w11, w21, w31 is. So that means you can see that I have just taken -10, +10 and +10 as an arbitrary value, and you see I have only one output because the class level is defined by a single scalar value. So that's why I have kept only one output y. But before that, it should go through this summer unit that will basically sum between xi and wi1, and then we will apply the activation function, and then we will get the output, and then only we can compute what should be the actual value and what is the actual value. Depends on the error of between them, we can continue. So let's see. You see, what is this u? U is wi1 into w into xi. Yes, for, I'm sorry, it should not be j, it should be I equal to 1 to 3. So if you just, that means 121 into -10 plus 16.8 into 10 plus 1 into 10. If you just add them, you will get this value, -1032. Now this -1032 is the value of u, and after this we have this activation sum function, and we can see this activation function is a signum function, and by definition the signum function say that if it is lesser than 0, output is -1. So here the output is -1. So that means I've got output y as -1. But with respect to this particular fruit, the class level is +1. So difference between these two is the error. So you see, if you continue with that, if you find the error and then you calculate this, if you just, since we know that what is the exact the definition of this, what is the exact formulation of the del wij, we have seen in my previous slide. That's why I have directly written that, considering eta as some value. I cannot remember right now what eta I considered some, maybe 0.1 or 0.01 I have considered, and then we have seen that del wij is nothing but this. So what will happen? So naturally this -10 will be added with this del w1j, then this 10 will be added with 0.336. So these are the correction values which will be added with the previous w, so that I can get the next w. So this W11, W21 and W31 gets modified by this from minus 10 it becomes minus 7.58, from 10 it becomes 10.336 and so on. And how we can use these values? We can use these values for the next pattern, because next time when the loop will run again, next time I will take the second pattern, and this second pattern will follow in the same way. But here now W11, W21 and W31 become the new value of W11, 21 and 31, and depends on that we will calculate something, and then we will get some y again. That, as for example, with respect to this trivial example we have seen, we have got y1 as minus 1 again. So here also the class is plus 1. So again we have some error, and depends on that some w1 will be calculated, and then we have got again new value of w1 and w211 and w11, w21. By the way, I had a mistake here, it should be w21, it should be w21. So now you see, in this way, as you will go on with these different patterns, these weights will getting updated and will be tuned much more, so that in future there is a possibility we can find the correct, exact correct value of the correct class level that I want. So in this way, it will continue for uh, mm, it will continue for the next time, for this pattern, and maybe many more. So I have just taken this first two pattern as an example, and I've not, I'm not actually considering these two pattern again, because ultimately if you understand the philosophy of learning it and weight correction, so you can understand for not only these four patterns, even 400 patterns or 4000 patterns, the philosophy is same. So in this way, basically, we can learn a new. We can learn. We can see how a single layer perceptron can learn a model, so that we can find the correct classification for some unknown cases. So okay.